Okay, so last section of the unit, 2.7, general results for polynomial equations. So all things polynomials continues. All right, just as a guiding question, for a polynomial function, we know that p of 2 is equal to 3. What can you determine? So a couple things that you should be recognizing from this. So the remainder, when you're given polynomial, is divided by x minus 2 is 3. Okay, that's your remainder theorem. If we think in terms of synthetic division, if I set up synthetic, then my remainder would be 3. Okay, I don't know what the polynomial is, I don't know what the quotient is, but I know the divisor and the remainder. So if I know that p of negative 1 is equal to 0, this is at least the third time we've actually written it out. X equals negative 1 is a root. And if it's a root, then it's a solution, an x-intercept, or a 0. We know x plus 1 is a factor of p of x. And this is really the biggest one for this lesson. Okay, so I know that I have a factor. And then the third, we said that the remainder is 0. And I'm sort of going to add to this because if we're graphing, I also know the point negative 1, 0 is on the graph of p of x. But that sort of reiterates the fact that it's an x-intercept. Okay, so really the first two are the most important, and then if we stick with the remainder theorem though, that's an important piece of information as well. Okay, so fundamental theorem of algebra. An nth degree polynomial has n roots, including real, imaginary, and multiples. And so we know real numbers, okay? Real can be rational or irrational. Imaginary has to include I. Whoop. So that can be in the form a plus bi. And multiples, an example of that is a double root when we see a factor raised to the second power. Or it can be a factor raised to the third power. Okay, so when the exponent on the individual factor is bigger than 1, that's what a multiple root is. Nth degree, n roots. The roots themselves are not the hard thing to determine. So when I look at g of x, this is a third degree polynomial. So this has 3 roots total. And that's real, imaginary, and multiple. H of x is a 4th degree polynomial, so this will have at most 4 roots. How many roots, including multiple roots separately, would a polynomial equation of degree 10 have? Degree equals number of roots. So a 10th degree polynomial would have 10 roots. This theorem is a good check to yourself, especially now that you have the ability to find imaginary roots. So when we add up all our answers, it better equal the degree of the function. And we have used this already throughout the course of the year. Complex conjugate theorem. Okay, complex conjugates we studied in Unit 1 when we first looked at Lesson 1.5. Okay, when we were first looking at imaginary numbers. If a plus bi is a root of a polynomial function with real coefficients, that means I need my polynomial to have real coefficients. So if you remember when we were preparing for the test, the Unit 1 test, you used the quadratic formula on a quadratic that looked like that, where a and b were imaginary coefficients. Okay, so this theorem only applies to any function that has real coefficients. And that can include an irrational coefficient, okay? But it can't include anything that would involve I in the expression. So when we go to solve, if a plus bi is a root of the polynomial, then a minus bi is also a root. So remember that these guys were called complex conjugates, where we just changed the imaginary term, and complex conjugates always occur in pairs. And this shouldn't seem foreign to you. Whenever we have an imaginary answer, it was always x equals, plus or minus 3i. Or we would have, if we used imaginary and we were left with x minus 4 squared equals square root of negative 5. Let me change that. Would equal negative 5. Then when we went to solve that, okay, x minus 4 equals, we take the square root, so it was always plus or minus. And then when we take the square root of a negative, we need I in there. Equals plus or minus I root 5. And then when we finally went to solve for x, here's our a plus or minus I root 5. And that plus or minus means there was two of them. They occurred in a pair. So whenever we deal with imaginary solutions, they always occur in pairs. And this is very important for when we go to actually use these to determine the equation of a polynomial. So if 1 plus I is one root of a polynomial, what's another root? X equals 1 minus I, because that's its complex conjugate pair. All right, so irrational conjugates. If a plus square root of b is a root of a polynomial function with rational coefficients, then a minus root b is also a root. So now functions like this have to be in the form with rational coefficients. Okay, so remember that rational means any number that can be written as a fraction. Okay, so I could have negative 1/4 x cubed plus 9x squared minus 4. Okay, I couldn't have something that looks like square root of 3x squared plus 2/3 x minus 1. You have to have rational coefficients. If a 6-degree polynomial equation with rational coefficients has negative 2 plus root 5 as a root, what's another root? So if we know that this is an answer, then the irrational conjugate is negative 2 minus root 5. So hopefully you're seeing all you change here is the sign in front of the radical. Okay, just like on the previous one, a complex conjugate, I just changed the sign in front of the imaginary part. Okay, we don't change anything except the operation between the imaginary or the irrational part of the root. And we'll look at equations on how these are going to be useful, but just be comfortable with determining the pairs. All right, odd degree theorem. If p of x has an odd degree, then there's at least one real root. So no matter what type of odd degree it is, there's always going to be one real root. So if I go to solve an equation that looks like this, add 1 to both sides, and I take the cube root of 1, and 1 is my only real root. So if this is all I get mathematically, then according to our root theorem, the first thing we looked at, there must be two imaginary roots. Okay, and we haven't talked necessarily about how to find those yet. But this is what you have to understand from that degree theorem. If this is a third degree polynomial, then there's 3 total roots, including real and imaginary. Because this is an odd degree, I can definitely find a real root, which means 2 imaginary roots exist. So here's a polynomial with an even degree, x squared plus 4. I attempted to find the roots of this equation. I set my polynomial equal to 0. I subtract 4 from both sides. But now when I take the square root, I get plus or minus 2i. So this is a second degree polynomial telling me that there's two roots total, but both roots happen to be imaginary. So odd degree, you have to get one real answer at least. And even degree, you don't necessarily have to get a real root to exist. Okay, sum and product of roots. If I have a polynomial, okay, of nth degree, 3 coefficients in particular are important. So let's change our color here. A is our lead coefficient. That's not new to us. C is our constant term. That's not new to us. Now we need B in here. And notice the relationship of B. So the coefficient of B is the coefficient to the term that's 1 less than the degree of the function. So if my degree is n and the lead coefficient is a, then b comes from the coefficient. The power is going to be 1 less than the degree of the original. Okay, so the sum of the roots. So if I solve some polynomial, I get whatever the solutions are, and then I add those roots together, they're always going to equal negative b over 2a, or excuse me, negative b over a, where negative b is the coefficient to the second term and a is the lead coefficient. The product of the roots. So again, I'm solving some polynomial using all the methods that we've learned this chapter. The product of the roots is c over a. C is the constant term divided by the lead coefficient if n is even. And the product of the roots would be negative c over a if n is odd. And remember that n is the degree of the polynomial. So we're going to do 2 quick examples together. Here I have a quadratic polynomial and g of x is a cubic polynomial. So find the sum and product. So according to my theorem, the sum is going to be negative b over a. Okay, so a, b, c. So the sum should be negative 8 divided by 1. So the sum of the roots better be negative 8. When I factor f of x, factors of 15 that add to 8. So I get x equals negative 5 and x equals negative 3. When I add those two together, negative 5 plus negative 3, I do in fact get negative 8 as an answer. The product of the roots. So since n is even, the product should be c over a. So constant term over lead coefficient. So that should be the product of the roots. I go back to my solutions. Negative 5 times negative 3 is in fact 15. All right, so for the interest of time, I would like you, we'll do g of x in class next time we see each other, but I would like you for homework to complete this chart. So given these 4 polynomials, find the sum of the roots and the product of the roots.